network science, machine learning, theory and applications in areas including health, e-commerce, cloud computing, internet advertising, and fairness. He is an associate editor of the ACM Transactions on Algorithms, editor-in-chief from 2014 to 2020, and an editor for the Theory of Computing, managing editor from 2006 to 2019, as well as the editor for Journal of the IISc. He is an elected fellow of 6 professional societies, ACM, AAAS, IEEE, AMS, EATCS, and SIAM. He was elected a member of Academia Europea and the Academy of Europe in 2018. He received a Distinguished Alumnus Award from his alma mater, IIT Madras, and he is a recipient of the Stratfor Prize and a Danny Lewin Award. So please join me in welcoming Aravind.
Thank you. Thank you, Kevin, and thanks everybody for coming here. I'd particularly like to thank you for inviting me and Boeing Corporation for making this possible. So let's please keep the talk interactive. Stop me at any time if you have questions. There is something which is the following, which is that I've put more material. I have put more material here than I can cover in an hour for a deliberate reason, which is, so I will certainly go over some slides a little bit fast, but since this is being recorded, I thought particularly for students and those new to the field, since it's recorded, you can pause the video at that point, and if you have any questions, feel free to ask me during or after the talk, or send me email. So we will go over some of the slides fast, but I hope to give the big picture, which is the unifying role of probability in a range of areas. And they span in this talk computer science, data science, and public health, but in many associated areas as well. So there are at least 2 interpretations of probability we'll take in this talk. The first one can consider as probabilistic models, where you assume that the input to the problem or the model that you're considering is probabilistic in some sense. For example, in machine learning, there's a range of models in which probability is baked in, like logistic regression, models for noise in a variety of phenomena. In the areas of disease diffusion that I'll talk about, again, probability is fundamental, and in Bayesian reasoning and so on. But also, you can imagine making your algorithm randomized. So you may or may not make a probabilistic assumption about the input, but you allow your algorithm to make random choices while it runs. And this again has numerous applications. I've put down a few here. I'll just mention one. As you know, privacy and security are very big issues, understandably. And one of the most popular, both scientifically and in practice with companies like Apple and others, notions of privacy is called differential privacy, where again probability is baked into the definition. This is an algorithmic technique, a randomized algorithmic technique, and understanding stochastic processes, which many of you do very well, is a huge win in areas like this, right? So we will think of randomness in both of these contexts as part of the talk. An outline of the talk is as follows. Please take a look. So let's start with the most theoretical part of the talk on a very simple but extremely powerful probabilistic lemma called the Lovasz Local Lemma. Okay, so we'll start with that. I'll probably spend the bulk of the time, maybe like 20 minutes on this, and then, but I hope to spend a reasonable amount of time on the rest of the topics as well. Okay, and specifically we'll be interested in the algorithmic aspects of this classical lemma. So it's not very classical, it's it's from 1975. It was formulated by Erdős and Lovasz, as you may know, 2 very well-known Hungarian mathematicians. But it's called the Lovasz Local Lemma because Erdős would go to talks and say that, this actually appears as a lemma in a seminal paper by the 2 of them. But Erdős would often say, and I have myself seen him say, that the lemma is entirely due to Lovasz. So he himself would call it the Lovasz Local Lemma. Right? We will see what it is in a few minutes. It has numerous applications. The key point is this: since many of you are mathematicians or have a strong interest in math, what the local lemma illustrates in many of its applications in graph coloring, resource allocation, packet scheduling and routing in networks, in game theoretic models, in many of these, it gives a great illustration of what is called the probabilistic method, which was pioneered by Paul Erdős. What this is really proving entirely deterministic statements using probability as a tool. So for instance, if you want to prove that a certain discrete structure exists, you place some probability distribution on all structures and prove that your desired structure S emerges with some positive probability. The probability could be very small, but it's strictly non-zero, right? Which means that the structure exists, right? I mean, this looks like a very trivial or kind of a useless almost, or it's not clear why such a general should work. But in fact, Erdős, who had a lot of innate faith in all kinds of sort of amazing directions, he was initially the lone voice when he initiated this area around 1948, and by now it's an absolute staple of computer science and discrete math. And the local lemma is an excellent illustration of the probabilistic method. And what specifically speak about this, when the lemma was discovered, it really was about proving the existence of a needle in a haystack, right? The algorithmic aspect was really not there. And around 12 years ago, Moser and Tadeusz developed a very, very nice algorithmic aspect of this. And we'll talk about how we can build on it further. We will speak about the resolution of some open problems from there, as well as some new applications. Okay, so to illustrate the local lemma, let's talk about a fundamental combinatorial optimization problem that appears in numerous applications as well, right? So this is called the satisfiability problem. Okay, so here you're given some Boolean variables. So in this case, let's say they are x1 through x4, each can be true or false, and the complement of each of them respectively I'll denote by xi prime and written in blue. So if x2 is true if and only if x2 prime is false. Okay, so the blue xi prime is just the complement, because PowerPoint doesn't easily allow the kind of symbol I want. I used it like this. Okay, you also have constraints, right? These are the constraints or clauses. For example, the first constraint says that either x1 is true or x3 prime is true, which is equivalent to x3 is false, or x4 is true. Okay, so you have a few constraints. Okay, and similarly, the second constraint says that you either x2 prime is true, that is x2 is false, or x3 is true, or x4 is false, etc. Right? In this case, you have three constraints: the first, second, and the third. Each constraint without loss of generality is an OR, right? You only have ORs, and you want all of them to be true, so you have an AND of OR problem, right? For those who in this is a canonical satisfiability problem called the conjunctive normal form satisfiability. Okay, so in this case, every clause or every constraint has size exactly 3. We'll call that K, right? So this problem in general is called K-sat, and this is an example of a 3-sat problem because every constraint or clause has exactly 3 variables, right? Keep in mind this parameter K. Yeah, so the question is this, right? You have 4 Boolean variables along with their complements, the respective complements. You have a bunch of constraints, in this case 3 constraints, each of which is an OR of some of the variables and their complements. The question is there a Boolean assignment to your underlying variables x1 through x4 that simultaneously satisfies all of these constraints? Okay, this is a very, very fundamental problem. I'll briefly mention some applications in a minute. Right? In this case, the answer is yes. For example, if you set x1 to true, that already makes the first constraint true, right? Because every constraint is an OR. So if you make x1 to true, the first constraint is automatically true. And then if you set x2 to false, it makes the second constraint true, and so on, right? So you can see that this is what is called a satisfying assignment. But of course, as you can imagine, a bunch of constraints may be inconsistent. They may not be satisfiable, right? So this is the canonical example of what is called an NP-complete problem. These are problems for which for very, very strong mathematical reasons, we do not expect any efficient algorithms, right? This satisfiability problem, and again, this is an example of with 3 sets. Okay, this has numerous applications. For example, in manufacturing and supply chains, so for instance, or if you're, operating an airline or something, you have various constraints, right? Like refueling constraints, staffing constraints, all kinds, right? All of them, and then you want all of these to be satisfied, right? And of course, you also have some budget constraint, all of these. In general, everything can be transformed to this. In general, many types of interesting constraint satisfaction problems can be reduced to this form of a bunch of OR constraints that you have ANDed together. You want all of them to hold. And the question is, can I assign my, say, staffing and refueling decisions and various budget decisions, how to split my budget between different operating units, etc., in order to satisfy everything I want, right? It's a true or false question. Unfortunately, like I said, it turns out to be NP complete. It's in fact among the very first problems shown to be NP complete in the early 1970s. So the problem is in general computationally intractable. So one reasonable question you can ask is, given such a bunch of constraints over some Boolean variables, is there some good sufficient condition that guarantees that the given problem is satisfiable, that there exists a satisfying assignment? And that's where the local lemma, as we'll see in the next slide, helps us. Okay, so and this is where the Erdős magic happens, right? This is a purely deterministic question, right? You're given a Boolean formula like this with a bunch of constraints, is it satisfiable or not? There's no probability here. But the Erdős magic, what has come to be known as Erdős magic, is we will assign the variables probabilistically in some way and prove, if you want a sufficient condition, that if the given problem satisfies certain conditions, certain sufficient conditions, then the probability that I simultaneously satisfy all constraints is positive. Okay, so then that's all you want, right? All right. So yeah. So somehow we are going to assign the truth values, the Boolean values randomly in some fashion, right? And show, assuming that the formula has certain nice structure, that the probability that all the constraints are satisfied simultaneously by your random assignment is strictly non-zero. Right now, we don't care how large the probability is, we just want it to be non-zero, right? This is the Erdős magic or the probabilistic method, right? In fact, while there are in general much more complicated approaches to assign the truth values, I'm going to look at the simplest way in which you can set the truth values, which appears very naive, but actually it's very powerful in this case, which is simply set the variables randomly. In other words, set each of them to be true or false independently of each other, right? The simplest random approach that you can imagine, right? The question is, can you prove under certain conditions that this satisfies all the constraints simultaneously? Yeah. Yes, you want some very simple condition on the clauses that will make it happen. And as we'll see, it's a very local condition. In fact, it's very interesting, since many of you are interested in physics and so on, this has some very nice connections to statistical physics and so on. I think in the Soviet literature by Dobrushin and others, there have been some related developments. Yeah. So let me just point out one thing which will be useful in the next slide. If you do the simplest random assignment, then notice that the probability that the first clause is violated, right? The first clause will be violated if and only if x1 is made false, x3 is made true, and x4 is made false, right? Right? This is false, that is true, and that is false, and the probability of that happening is half times half times half, 1/8, right? In general, if you had k-sat, if you had k terms here, the probability of that would be 2 to the minus k, the chance that you violate a particular constraint. But the number of constraints can be, say 10 million, and these constraints are not independent of each other, right? They overlap on variables and so on. So you cannot say the chance that, okay, so the probability that the first constraint is satisfied is 1 minus 1/8, which is 7/8, right? You cannot argue that therefore the chance that all the constraints are satisfied is just 7/8 to the power of the number of constraints, because they're not independent of each other. They overlap on variables and so on, obviously, right? But that's where the local lemma, which we'll talk about next. So what is the local lemma? Let me now state it in a slightly more general context, right? So the local lemma says the following. Suppose you have some underlying independent random variables x1 through xn. These need not be binary. They can take values from general domains. And suppose you have bad events, let's call them E1 through EM. Please note the distinction between N and M here, right? So right? So each EI is a function of some subset of the xj's. It's some Boolean function of some subset of the xj's. For example, E1 here could be a Boolean function of x5 and x8. E2 could be a Boolean function of x2, x5, and x10, and so on, right? So each share a variable. They share x5, right? Because they share the variable x1. But E1 and E4 do not, because their variables are disjoint, right? Their variable sets are disjoint, right? Okay, good. So now let's think abstractly. You have a bunch of independent random variables xj and some Boolean functions ei of these, right? And the local lemmas, in fact, there is a more general version that I'll briefly talk about. The symmetric version of the local lemma says the following amazing thing, and you'll see why the word local comes up immediately. It says if you have the following two uniform upper bounds, right? If you're told that every one of the EIs is probability, so think of these EIs as bad events, okay? You do not want them to happen. For example, EI is the event that clause I is violated, right, by your random assignment, right? If each bad event has a uniform upper bound of P, and furthermore, each EI depends on at most D others, right, for some parameters P and D, then as long as P and D are kind of reciprocally related up to the factor E, this is the standard E, right, 2.71. As long as this is true, and in fact the constant E is best possible here, you cannot improve upon it, then in fact, with positive probability, all the EI are simultaneously avoided, which is what we want, right? What is amazing about this is that you can think of this D as a constant, okay? So you can think of P and D as constants. For instance, maybe P is like 1 in 50, and D is like 3 or whatever, right? In which case this inequality will be true, right? But notice this doesn't say anything about the total number of bad events M. That could be a billion, right? This is a totally local condition, right? It says take an event here, look at its probability of happening, and just count how many neighboring events it has. It is something totally local. It's like atoms interacting locally with their neighbors in a lattice or something like that, right? You have some totally local interaction model, and as long as you have some simple local conditions like this, right, then regardless of how many events you have, the probability that all the bad events are avoided is strictly positive, right? And again, the constant E is in general best possible, right? It's a truly amazing lemma because there is no connect. In fact, the point is this. I'm going a little slow, but that's okay. I'd really like you to all to get the basic message, and then we can go a little faster elsewhere, right? The point is, I said, suppose P is like 1 in 50, right? So what is P? It's the probability of a particular bad event happening. Then by the linearity of expectation, remember, you have M bad events, right? You have M bad events, and suppose M is a billion, right? You have a billion bad events. Each has probability 1/50th of happening. Then remember, the expected value function is linear, right? You don't need independence among the EIs, anything. Then you immediately know that the expected number of bad events is 1/50th of a billion, which is 20 million, right? Right? You expect 20 million of these billion events to happen, right? But you are still able to show that with positive probability, in fact, none of them will happen, right? That's a very surprising phenomenon, right? So if you expect 20 billion, you probably expect that with with essentially it's concentrated between, say, 20 million, say 1 million and 100 million or something. But in fact, even the very smallest point, which is 0 of the number of bad events, is actually achieved, right? Right? So that's great. So the local lemma has numerous applications. For example, so let's in fact see an immediate application here, right? So like we saw last time, if you have an instance of ksat, right, the simplest Erdős magic you can apply is just randomly assign the variables. And as we saw, the probability that any one particular clause is violated, which is our parameter p, is 2 to the minus k, right? Like in the previous slide, k was equal to 3. And then if you do the simple algebra here, if you're given p, what should d be? D should be whatever, 1 over ep minus 1, right? So as long as d is at most this, in particular, if you have a bunch of clauses and no clause or constraint overlaps more than this constant amount of others, then even the total global formula is satisfied, right? And this condition again is in general best possible, okay? So It's really, really amazing. These are in general, the most powerful sufficient conditions known for satisfiability, as well as for many totally seemingly unrelated problems. Okay. In any case, the symmetric version of the local lemma is just this. In fact, it's a little more general than this, but let's just look at this. Okay. Right. So it looks great. Right. In general, it's best possible and so on. So what's the catch? The catch is, unfortunately, the probability the probability that this actually happens is unfortunately inherently exponentially small, right? Remember, we have the two parameters n and m. We'll in fact distinguish them carefully very soon. But in the efficient algorithms, what we want is an algorithm that runs in time polynomial in n and m, right? That's the general notion of an efficient algorithm, right? But unfortunately, this probability can be exponentially small in m, okay? Which means that if you really want this to succeed, you have to repeat this random process exponentially many times in m. That's not going to be feasible. If m is even like 200, e to the 200 is an infeasibly large number, right? So the catch is that although all the local lemma is guaranteeing is the existence of a needle in a haystack. The question is how to. In other words, what's the algorithmic aspect of the local lemma? So because of this inherently small probability, it was when the lemma was developed in 1975, people in general thought that it's a hopeless problem. But there was slow progress starting from the early 90s, culminating in this amazing work of Moser and Tardosh, which in fact gives a very simple algorithm to actually construct a structure that, with high probability, that avoids all the bad events. What is that? It's perhaps the simplest algorithm one can think of. It's just this, okay? Okay, again, remember the general abstract setup is you have these independent random variables and you have a bunch of bad events. Each EI is a function of some subset. For example, E5 could be a function of x1, x10, and x100, okay, and so on, right? So you have this abstract setup, right? And you want to find, what do you want to find? You want to find an assignment to each of these variables, x1 through xn, that you can certify avoids all the bad events simultaneously. For example, you want to assign one Boolean value to each of your variables so that all the constraints are simultaneously satisfied, right? That's what you want to do, right? So the simplest algorithm is this beautiful algorithm by Moser and Tardosh. Yeah, so basically initialize the random variables from their respective distributions. They're independent, right? Sample them independently from their distributions. If they avoid all the bad events, great, you're done, right? But typically some bad event EI will currently be true with respect to the current assignment to the variables, right? For instance, if many of them are currently true, unfortunately, just pick one of them arbitrarily. For example, I said that E5 depends on x1, x10, and x100, right? Pick E5 if it's currently true. That's something you don't want, right? E5 depends on x1, x10, and x100, right? Just resample these variables from their respective distributions independently. That's it, right? The simplest kind of iterative algorithm, iterative repair kind of algorithm that you can imagine. Of course, as you can imagine, if you repair E5, you may end up screwing up E7, right? And so on, obviously, right? So what's the guarantee that this simple kind of algorithm can terminate? The amazing thing is, Moser Tardosh show that, in fact, the expected number of iterations this algorithm takes is just only O of m, right? So that looks terrific, right? It solves many, many problems, in particular the KSAT-like algorithmic problem. This is a randomized algorithm. Note that sampling is fundamental to this algorithm. It's randomized, right? So what's the catch again, right? Are we done? Unfortunately, no. And this is where our work comes in. There are two issues. First of all, okay, so what really do we want of our problem? So if you recall what I said, the output of our algorithm is really one value for each xj, right? Set x1 to this, set x2 to this, set x3 to this, and so on, right? Right? So in other words, the output size of our algorithm is of the order of n, right? The number of constraints, m, could even be exponentially, could be implicitly specified. For example, you don't need to write them down, they may be implicitly specified, and all you want is, so your output size is only n. So this order m that you find here may be too large, right? Maybe in fact exponentially large. That's one issue. But the even harder problem is, notice that the algorithm says, so now suppose there are exponentially many constraints, right? Notice that the algorithm says, pick out one constraint, one EI that is currently true. Picking out such an EI could be an NP-complete problem, or in some, right? So certifying that either no EI is currently true or picking out an EI that is currently true can itself be a computationally intractable problem. So it's not clear how we can run this algorithm, right? So, and in fact, both of these appear in some fairness type applications. So I'll go a little bit faster now. Does everybody understand the basic setup? Right. So I will have to skip some details, but I hope that the main message is clear, right? So yeah, so we, in a couple of papers, one with Heupler and Shaha, we showed the following: that in fact both of these issues can be bypassed. So in general, like I said, what we saw was what is called the symmetric or basic version of the local lemma. There is a more general version, right? And what we showed is that by allowing a small slack in the exponent, 1 minus epsilon, where epsilon is any positive constant, say 0.01, you can actually solve all of these issues with Moser-Tardouche. So essentially, this makes all the known remaining open questions with making applications of the local lemma algorithmic. It makes them algorithmic, except for what is called the lopsided local lemma, which we handled in a later paper, right? So yeah, so the other thing we show, in fact, is some bounds on. If you run Moser and Tardouche, it produces a distribution on the output of the XJ. Right? Can you say some things about the output distribution of Moser Tardouche? That's the more general theorem we show. This is something we show. Again, I'll go over this a little bit fast, but I'll just say that. So basically, what we're saying is for any event A, if D is the output distribution of Moser-Tardouche, we are able to relate the conditional distribution of the probability of A conditional on it being the terminal distribution of D with its unconditional probability. And that turns out to have several applications. For example, one nice application is, I said that the local lemma applies when you want none of the bad events to be true. But what say, you know what, that's a very hard problem. I'll allow a small, maybe 1% of the bad events to be true, right? In that case, essentially nothing was known. We are able to develop a constructive version, an algorithmic version, where even a non-constructive version was not available. In particular, what we show something like this. Basically, if each EI bad event depends on something like this number of other bad events, then you don't avoid all the violated events, but you are able to bound the expected number of violated events, something like this. So this is new even in the non-constructive world. So I'm again going a little fast. If you don't get all of it, okay, this is recorded, so you'll slide. But yeah, so basically what I want to say is that both of these issues with Moser-Tardouche can be resolved, and this is the work with Heupler and Shaha. And then I did some later. Yes, please. Ah. Oh, very good. Yeah. Okay. Excellent. Yeah. So yes. So Nathan's question is, what is this? For example, in the KSAT problem, satisfiability problem, this kind of general asymmetric version of the local lemma is so we go back, so we can answer Nathan's question clearly, right? So the slack is this stuff, right? So the general asymmetric version of the local lemma is applicable when the constraints all have different lengths. So I said that everything has length k, right? But that's a simplifying assumption. More generally, if you have constraints of very different lengths, you use something like this, right? So the local lemma, the asymmetric version of the local lemma, will give a certain sufficient condition for the formula to be satisfiable. So here we have to make the sufficient condition a little bit stronger. Basically, if it says that this clause is allowed to overlap up to 100, this will make it overlap up to 95 other clauses, right? Good, thank you. So yeah, so that's the stack, right? So I will go a little bit faster here. And furthermore, I also worked on this with my former PhD student David Harris, actually, I should not say former grad student, because the famous mathematician Israel Gelfand used to say that, calling somebody your former student is like calling them your former child, calling your child your former child, which you don't want to do, right? Okay, with my graduated student David Harris, which appeared in this JSM 2019, we asked the question: in Mosa-Tadeusz, when an event EI is violated, you resample all its variables. What if you don't do that? Can you get some further improvements of the local lemma? Right now, you want to improve the lemma itself, right, and also get an algorithm from it. And the answer is yes. So recall that each bad event EI is determined by some subset of the variables, right? And when you detect that EI is currently true, you resample all of these, right? The question is, what if you resample only some appropriately random subset of this, right? But why should, can we avoid the sampling all of the SI, right? Then what you do is actually, we do some involved work on constructing a distribution on subsets of SI. And when you need to resample, you pick one of those at random from the appropriate distribution and only resample the subset. This leads to less interaction between the random variables and gets you better results. In fact, it leads to sort of new improved results, once again, even in the non-constructive world, but they give the solution constructively as well, right? And then we give various other, faster versions of the local lemma. All of this, we had a bunch of results, and one of them, the last one, is with a student, Antares Chen, who was then a high schooler working with me, and he's now doing his PhD at U Chicago. So to summarize this part of the talk, the emerging picture is that Mosa-Tadeusz is much more than just an algorithmic version of the local lemma, that it's a stochastic process of its own independent interest. By building on various aspects of it, one can get very powerful results, in some cases even going farther than the local lemma itself, right? And for example, there is a very nice paper of Moitra on this. I will stop this part of the talk here. I went longer than I planned, but I hope that, if not all the details, the basic setup is clear to you. Let me pause here and ask if there are further questions about this part of the talk. The later part are going to be more practical and, for some of you may be of more interest. This was the most theoretical part of the talk. Any further questions about this? You can also ask later, but it's a good time to segue to the other topics. Okay, so let's continue. The second part is on public health, and of course, it's on our minds very much these days, right? So the standard model in epidemiology is that you have a population, and if a person P is sick, they have the same probability of giving it to any other person, right? While this is a reasonable assumption in a tight population like a hospital ward, or a household or something, it's clearly not valid even if you look at a small town, right? Because if I'm sick, I'm only going to give it to people. Of course, they may then infect people they come in contact with and so on, but it's not at all the case that I have the same chance of directly infecting everybody. The traditional models, build differential equations. Once you make what is called this uniform mixing assumption, is that I'm equally likely to directly give it to anybody. This is the standard SIR setup, right? But the question we asked is, is that this does not take into account the complexity of human interactions and leads to relatively simple, therefore it leads to a relatively simplistic solution, right? The question is, in fact, networked epidemiology is about 150 years old, and Dr. John Snow, he's considered one of the pioneers of epidemiology. He found that so he was the person who found that cholera doesn't spread through the air or something, but through infected water, by placing water pumps in London, right? Or, well, the pumps were already deployed, but then he did a systematic study of who fell ill, which pump did they get water from, and so on. So he considered the kind of the in some ways one of the pioneer of epidemiology, but certainly networked epidemiology, right? Well, cholera is not the disease we want to consider here. We want to study viral transmission, although bacterial transmission is important, which I may speak about later. Yeah, this in particular proved that cholera spreads through water. Okay, so the work that we have been undertaking for the last close to 25 years is developing rich contact network models for how people interact with each other in various populations. For example, let's say in Seattle, or in fact, some of our work is based in Portland. And then develop good discrete agent-based simulations to simulate the spread of the probabilistic diffusion of the disease, the percolation of the disease, and then look at our very important algorithmic control approaches about who to vaccinate, where to monitor, where to put sensing equipment, and so on, how to do things proactively, ideally, right? So that's been our broad goal. I will skip over some of these details, how we construct the social networks and so on, but again, you'll see the slide if you want, and again, please add it. This was actually Portland data, through census data, land use data, transportation data, as well as simulations. We construct these and also cross-verify them through surveys. So I'll just speak about one aspect of our work with Eubank et al. That appeared in Nature a while, but if I may say so, and I say this without any without any conceit, because obviously research is a collaborative endeavor, and if we did something, it's because we were inspired by others. But I think it's without any sort of intent or bombast. I can say that this work is reasonably considered one of the kind of initial papers of networked epidemiology, which is now a very well studied topic. Of course, the problems are very hard. I'm not saying that we solved all the problems, but I would say that the initial formulation has had I would say a good impact that I'm personally satisfied with. Yeah. So I will just mention one thing. So there's a variety of things we did here, but there is a probabilistic model for network interactions, people's and other agents interactions, by developing Fan Chung Graham. You may have heard of her. I think she's she also spent some time in Vancouver these days. She's a very famous discrete mathematician who was at UCSD. She and her student Lincoln Liu, they developed this very nice probabilistic model for networked interactions. And in fact, this 1 plus little o of 1 means the following. We showed that for certain problems of where to deploy sensing equipment and so on, we cannot solve the problem optimally, but the little o of 1 is meant to indicate a quantity that tends to 0, right? You can solve the problem, the amount of sensing equipment model to within 1 plus epsilon of is the best possible, right? We developed these algorithms for early detection, surveillance, and so on, right? So a lot of this was done in cooperation with federal agencies, as you can imagine, the DHS, and so on. So I will skip over some of these details. Some of my theoretical work actually helped in earlier theoretical work actually helped with some of this. Yeah. So basically, the naive way of preventing diseases essentially leads to mass vaccination, right? Which is not a feasible thing. It can lead to panics and so on, right? Not with COVID, but right, let's say with milder things, a sort of very massive response, or mass vaccination is okay, but mass quarantining is not okay, right? I mean, it impacts the economy and so on, right? So what we showed is that, in fact, this leads to some, what we proved is that in a stochastic model of network contacts, in fact, a simple greedy algorithm to figure out where to do proactive surveillance can lead to much better solutions without closing down, without shutting down society, basically, right? So yeah. So in summary, this work, I'll speak about a few different of our networked epidemiology type projects. These random models that are verified with real world data, and algorithms for surveillance and prediction of where disease will spread and so on, right? The second project I'll say very briefly about, this was with Chris Barrett and others, and many from the same group as before, Eubank et al, right? So very often, in the presence of a disaster, you want the National Guard or the military, to go to the disaster zone, work in the local area during the day, and come back to a military base or something, right? So, well, these four are critical, right? Critical subpopulations, because their work is absolutely required. But when they go out into the infected area, they may get infected and infect each other and so on. So how to sequester them well in the military base? We developed some interesting dynamic programming algorithms, and in fact, there are some very nice open questions there for those of you who are interested in combinatorial optimization, right? How to carefully sequester them in different groups when they come back, subject to some simple testing that we do as they come back into the military base or so. This was studied for the DoD. The third, which we have been doing for a while, but is of much current interest, is optimizing vaccine distribution. Early on in the early stage of an epidemic, as you know, vaccines are limited. You have to release them in stages, right? How to schedule, the distribution of vaccine? There is one very nice, influential paper by Medlock and Galvani, which is kind of more demography based. So, for instance, you may say certainly everybody below 10, vaccinate people between 30 and 40 because they are likely to be parents of young children, right? And the young children may be bringing it, and also vaccinate people above 70, right? So it's a demography based strategy, right? For instance, this may be in some cases it may be a blunt weapon because you may have a district which is substantially composed of seniors. What do? Not give it to there, right? So can we again mine the contact network structure of the population better in order to have better targeting of how to distribute the vaccine stages? It's been something we have been studying for a while. It combines social contact networks and stochastic optimization. Stochasticity naturally comes here because disease spread is stochastic, and people's compliance, all of these are stochastic as well. I will just mention, there are the proactive vaccination or isolation-like problems, right, or surveillance-like problems. By the way, I'll just mention, as you know, of course, we are dealing with the coronavirus, which is a virus, right? But a very, very vital issue for present and future is what is called antimicrobial resistance, which is the fear of it's not a fear, it's a very legitimate concern of superbugs and so on, sort of antibiotic resistant bacteria, new mutants developing that we just cannot treat. And there again, some of them are infectious. So all these problems apply to any form of infectious disease. So originally when we started, it was for viral diseases, but this AMR, a very well-known example of an infectious bacterial disease is tuberculosis, but there are all these modern bacterial infections that come up in hospitals and so on, right? So those are also relevant. So I'll just mention two strands of work that we did. In fact, both got published this year. The first one, basically, again, for the Chunglu model of random interactions with a certain, it comes with an important parameter beta. We showed that when beta is greater than 3, there is an efficient algorithm to proactively monitor, some subpopulation. And we showed also some barriers. When beta is less than or equal to 3, we showed that certain algorithmic approaches will not work, right? So it's a nice open question to resolve it for beta greater than or equal to 3, if at all it's resolvable. And then now I'll talk about fairness, which is, I think, a vital aspect of, as we all agree, of modern AI and so on. Vaccine distribution is not necessarily equitable, and populations are mobile. Some people work 2 jobs and so on. How can we sort of distribute vaccine for a population whose mobility we have some reasonable understanding of, so that multiple demographic groups are relatively, at least, equitably served? There's some further work in that direction. In general, we learned a lot from COVID, which is that, disease modeling is a very hard problem. But we continue to work with various government partners, many of whom have been very nice, and tech partners like Google has supported some of our work. This whole work is supported by an NSF expedition grant, which we are very thankful for, and various other partners, right? So yeah, so now, the focus here is, of course, on good algorithms, but eventually they have to be deployable and interpretable and so on, right? The eventual description has to be pretty simple, right? So this is something we are very actively working on, and definitely expect to continue working on with antimicrobial resistance and so on, as well as to take a more integrated view of these, starting from the molecular basis of disease all the way up to social networks and psychology and so on. Okay, any questions about this part? Okay, so again, please stop me at any time if you have questions. We've had a few good questions so far, right? And so let's talk about individual fairness. By the way, let me highly recommend this book to you. It's by Mike Kearns and Aaron Roth, who are both at Penn. And this book is, in fact, for the educated public. If you know a high school senior or an undergrad, you can gift it to them. It's a really nice book without going into too much technical detail. It really brings out the complexity of how to build algorithms that are ethical, so to speak. Ethical, I mean seriously, right? So yeah, it's a major ongoing concern, right? So I will only speak about our work on fairness in one particular domain, in unsupervised machine learning. And in unsupervised machine learning, you may know that clustering is kind of the ubiquitous unsupervised ML algorithm, right? You have data points that a human has not labeled. For example, you may have access to a newspaper from 50 years ago from a language that is totally foreign, okay? And you can do NLP and so on. But let's say you have not understood this language well enough. You at least want to classify these news articles into, this is one cluster, perhaps this is on politics, another perhaps on sports and so on, right? Clustering comes up in numerous examples in bioinformatics and all kinds of other areas. The question is, are many clustering algorithms fair? Unfortunately not. So for instance, one classical objective is you're given a parameter k. This is called the k-center problem, right? You want to cluster your data into k or fewer clusters so that the maximum radius of any cluster is small, right? So very reasonable objective. Many other such objectives are possible, right? Now, so for example, in this picture here, there are naturally three clusters, right, given by the three colors. If anybody here cannot see a color, please let me know. I know that colorblind people sometimes cannot see, green kind of thing. If you want me to point it out on the screen, I can do that, right? So there are these three clusters, but there are also many outliers, right? So for example, this point, it can really go to this cluster or this or that, or it could be left out as an outlier, right? Usually, clustering algorithms also allow some budget for outliers. They want to cluster most of the points, but maybe 0.1% of the points are cast out as outliers, right? But the question is, it could be that because of the vagaries of tie breaking and so on, points that represent a particular demographic group may be much more impacted by this. Being cast as an outlier is the worst outcome in clustering, but also you could be misclassified, you could be far away from your cluster center and so on, right? I will go a little bit fast on this. I will skip over some, show you what our result is. We have done a few related projects on this, but here is one, okay? Consider this setup for handling outliers or in general. So what if you allow users to contract and saying that, I may be cast out outlier, but I want some kind of quality of service. I'm user J. I ask that the algorithm, which will be randomized, cluster me with probability at least Pj. It may be that the user is not asking this, but it may be the government or some regulation saying this, right? It could be, one can imagine various, and in fact, even more than individual fairness, we are interested in demographic fairness. If you do individual fairness, then by the linearity of expectation, you automatically do demographic fairness as well. Okay? So what we show is, for such problems, where you guarantee probabilistic individual, where you want to guarantee probabilistic individual or group fairness, right? So here is a theorem. Again, they're all my students: David Harris, Tommy Pinsel, Koa Trin. This appeared in 2019. What we showed is that either you can prove that the problem is infeasible, or you can get some very good guarantees, both for the clustering and for individual users. In particular, user J will unfortunately not be satisfied with probability Pj, but at least 1 minus epsilon times Pj, where you can trade running time with epsilon. If epsilon becomes smaller, you can still solve the problem, but the runtime becomes more. But in principle, we get polynomial time algorithms with such guarantees, which give you local plus global guarantees. This is a local guarantee. This is the classical global guarantee, right? Randomization as part of the algorithm naturally tries to give you both. So this is one approach to fairness that we have been addressing, which is you have a global objective which ideally you will satisfy with probability 1. Right? So no problem. That's guaranteed with probability 1. But you also have a local per user or per demographic group fairness ideal that you solve, that you get locally, right? So and randomization is the key bridge that connects the two of them, right? So we have a variety of ongoing projects. Fairness, I don't think we understand fairness at all well. there's an active conversation about fairness in multiple institutions, fairness in ML, fairness in AI in general, right? But it's an active area, and there's very interesting theory and practical work. And I'm very happy to. There's very nice interpretation for many of these as well. I will skip this because I want to talk about one more area that, so yeah, we've been working on fairness in a variety of contexts. You can see. I don't have time to talk about these here, but again, very happy to talk to you offline or by email and so on. Yeah, the one last area that my group is working on is data-driven or data science approaches, broadly in what you can consider e-commerce, cloud computing, digital advertising, so on. A company like Facebook or Google, offers the service free to us because it makes money through advertising, right? By showing us ads, and we click on them, and hopefully that gets converted for the company. So yes, like I said, the primary thing that many tech companies do to match. So for instance, there is a pool of ads. So user types, let's say, sports car on Google, right? And of course, Google then can quickly verify their location, and if they have a cookie, they know Google knows the person's various identifying information, attributes, and so on. And based on that, well, Google has a pool of, let's say, 200 ads it can show of local outlets where the person can go and check out cars, or online outlets and so on. And of them, it has to display, say, 5 of them, right? So or show 5 of them here, right? 5 should it show, right? What match should it give to this user who's arrived right now, right? So it's a very fundamental problem for a variety of for Uber, for instance, this user, which nearby driver should they be met, right, based on the characteristics of the driver and the passenger and so on, right? So yeah, so we our sort of our stream of work has we have considered improvements in expected revenue for the platform, as well as fairness for passengers as well as drivers and so on in rideshare kind of stuff. Yeah. So for instance, how to improve expected expected revenue for the platform when in a setting like rideshare, right? The driver, once they are assigned to a passenger, will be busy for a stochastic amount of time, and then will come back to the system, right? Or similarly, in a call center, a call center agent will be busy for some stochastic amount of time with the next customer, but they're going to come back. So this is a recurrent process, right? How do you do assignments or matching in such contexts is some work I did with my collaborators and with my colleagues and students. Other related work we did, you can look up some of these conferences, primary AI and machine learning conferences where we did some of this work. I will, before concluding, I'll just put up this slide. I've been very fortunate to work with a large number of diverse collaborators, and this is a sample of some of the work we are doing. Some of them that I did not speak about. By the way, the last bullet item is aspirational. I really would like to work on energy. I've had a few conversations, but I don't think I've made significant progress on those. But I'm very, very interested in this last bullet. But all the other bullets are ongoing work. I'm interested in antimicrobial resistance, this kind of stuff also, as well as fundamental questions in machine learning and so on, learning, this kind of stuff. I've been interested in sample complexity in machine learning for a long time. I did work around 2000, but I'd like to go back to that. Very interesting statistical stuff there. Yeah, so to conclude, I'm very happy to take questions again. I hope I've sort of given a glimpse that randomness can be a very powerful tool. We saw various applications in computer science, data science, public health, and so on. I acknowledge the impact the very positive impact my collaborators and students had on me. I thank all of them as well as our funding agencies. Let me stop here. Thank you. I see. Yeah. Very good. So, unsupervised learning can naturally lead to supervised learning in the following sense, right? Very often your data set may be 10 million points, but you're only able to label, to say, let's say, hire humans to label 5,000 of them or something, right? If you can cluster the data into 5,000 clusters, then the center of each cluster, this is called semi-supervised learning. You can hire somebody to just to look at all this. But let me answer a question you did not ask, which is, even in supervised learning, fairness is very important because, for instance, there have been some embarrassing, terrible things in face recognition and so on, right? First of all, the training set may not be rich enough. That already creates problems. But even if the training set is rich enough, right? For those of you who have seen supervised learning, you know that there is a global function called a loss function that the training algorithm is trained to minimize through convex optimization or something like that, right? But that's again a global objective. Essentially what it says is, I've seen, I have a bunch of hypotheses. I want to pick one of them, right? And I've seen a bunch of training examples with their labels, right? Give me one hypothesis from my large hypothesis set that minimizes the total error on these in some L2 sense or something like that, right? But if you just maximize the global objective, you may be doing very poorly on a certain given subpopulation. Can you enrich your objective so that the subpopulations are also served well, right? That's an Yes, that's true. Yeah. And the question is, what are the trade-offs? Suppose you want some max min kind of thing, that the minimum performance on, of course, as if you tune hyperparameters, it may make things worse for another subpopulation. You may be interested in a max min problem where the lowest quality of service that maybe you have 10 demographic groups, right, that it receives is at least this much, right? So you can solve all these through, sort of rigorous, fair approaches. So, thanks. Yes, yes, thank you. Yeah. So we are fortunate to have access to very significant supercomputing abilities. And as you saw in with COVID, we most often don't need real-time response, right? It's not like an ER kind of thing where real-time response is needed. I mean, if you want to announce, lockdown restrictions or prioritization of vaccination kind of thing, I mean, if you take a day off supercomputing time, that's normally okay, right? But yeah, I mean, so a good bridging model that is fast and realistic would be great. We are working on some of those, but I think we are still far away from that. But my answer to you is that our bigger worries are model accuracy and so on. So far, running time seems to be less of an issue because of the non-real-time aspect of many of these problems. Does that make sense? Yes, yes, thank you. Yeah. So there are two questions. What about how do you construct good models for the network? And what about the probability of diffusion, right? The probability of diffusion is the easier question to answer. As a first approximation, we take it as the same value p, although for some of our applications, you can take it to be some diverse kind of, heterogeneous values, right? The network structure, so if you have a model, what is one way of testing the model, right? Well, the model has some built-in features, right? But it also has some non-built-in attributes, right? Okay, so for instance, if real-world networks satisfy properties P1, P2, and P3, and your network model was only built to satisfy P1, it may or may not satisfy P2 and P3, one good sanity check is whether it also satisfies P2 and P3 which are not implied by the probabilistic construction of the model, right? For instance, there is what is called the clustering coefficient, which statistical physics and so on also is very interested in, right? Which is about local clustering of people, right? And that's not, for example, the Chung-Lu model says nothing about whether the clustering coefficient should be this much or not. But thankfully, a lot of this matches actual data, right? But yeah, so it is true that, and in fact, Chung-Lu was in fact originally discovered for the internet's autonomous system level network, and it just thankfully turned out to work here. We don't at all know enough about human mobility and connections to have a very first principles approach to model building. It's much more about taking reasonable models and then seeing how many real world properties they actually satisfy, right? So that's an active area of research. Yeah. Excellent, excellent. Okay, excellent, excellent. Let me go back to the slide. Thank you for that question. Yeah, we can answer that. Let's look at this Portland slide. Yeah, right. So here you have a graph, a network, where the nodes on the left correspond to people, let's say in Portland. The right-hand side is about locations they visit in a day, and locations include public transport and so on, because it's big in Portland, right? So, right now, the degree distributions that turn out to be appropriate is uh, a power law degree distribution on the right-hand side, as you point out, and something like Poisson with a small mean for the left-hand side. Yeah, yeah. That's a very good question. Yeah, Chung-Lu assumes that these are independent, which in general is not, I mean, you bring in some dependence by these Poisson type things, right? But I don't think we understand correlations at all well. It's a very good point. Yeah.